Okay, so the topic for today, we got one really important thing to cover. So I'm going to skip around a little bit. I'm going to skip around a little bit and just hit the highlights. Okay, but this is one you got to know. So what if we were asked to do something like this? Find the area enclosed by the graph of the relation x to the fourth plus y squared equals 1, which looks like that, right? So how would we do this? We'd probably break it up into fourths because there's symmetry here, right? And we'd probably just take the top half of this, which is, if I just took this part right here, that would be the function. If I solve for y squared, I get y squared equals 1 minus x to the fourth. And then I'd square root both sides and get y equals plus or minus the square root of 1 minus x to the fourth. And that's what this one would be. Y equals positive the square root of 1 minus x to the fourth. And we would just integrate that from 0 to 1, right? And we could find that area and then multiply it by 4, right? No big deal. So I'd get 4 times that integral. Okay, but the problem is this exact area cannot be found using calculus because that function, that square root of 1 minus x to the fourth, is not an integrable function. There is no elementary function that you can play calculus Jeopardy with and get that result. It doesn't exist. So that's kind of weird that there are some functions like that in calculus. You can differentiate anything, right, using the correct rules. I mean, you can find a rule and differentiate anything, but you can't anti-differentiate or integrate anything, which is a little strange. Okay, obviously we have to be able to find an area. And so what we have to do is we have to use numerical analysis. We have to find an approximate area and just make it good enough that it suits our purposes. Okay, so we've done stuff like this, right? This is gonna be a pretty quick section for us because we've already talked about stuff like this. Remember when we developed the idea of the integral, what did we do? We just summed up a bunch of rectangles and we let the number of rectangles go to infinity, right? Now the thing is, we were able to use rectangles because we were able to take that limit as n goes to infinity. And even though rectangles may not have matched the function very well, right? Because rectangles don't match a steeply inclined function. Something that's got high slopes don't match that, the horizontal tops of rectangles very well. But again, because we could let the number of rectangles go to infinity, we didn't care because we were going to get an exact answer anyway. But the problem is we couldn't do that for something like this because when we try to take that limit as n goes to infinity, it would blow up. It wouldn't work. Something that's not integrable means that you can't take that limit as n goes to infinity. So what we're going to want to do here is not use rectangles. We want to use some kind of a function that matches the curvature better than rectangles because we can't take an infinite number of these things, right? Okay, so how would we go about doing that? Well, I'm just going to put some stuff in here. No, this is only going to be for notes. I'm not going to cover this in class. I just went through it. If I had time, I would review like the midpoint formula or the midpoint rule for estimating areas under curves, but it's really not that important. Even though it says super important, it's really not that important. If you have some time, which you don't, but if you do, look this over. I'll put this in the notes. Like over the summer, if you're bored, go back and pull this up and look at this, and it'd be good practice. But I'm not gonna go there today. So what I want to do instead is let's pick a shape that's easy to add up. Well, we'd like to pick something that's geometric, meaning it has all straight sides. So we can use a geometric formula to add it up instead of having some complicated shape that has a curved top, which would be more complicated, right? That would require calculus to add up the area of each individual shape, which is going to be a pain. We don't want to do that. So let's pick a trapezoid, right? A trapezoid would make sense. It would be just like our previous rectangles, only we'll tilt the top of this thing so it matches the slope of the function better. Everybody get that? That's a better shape than a rectangle. It's much more efficient, okay? So we just need to remember, well, how do we add up the area of a trapezoid? Rectangles are easy, just width times height, right? But what about trapezoids? Well, think about how we add up trapezoids here. All we do with a trapezoid, what's the definition of a trapezoid? It's a quadrilateral with what? Well, quadrilateral means 4 sides. Okay. A quadrilateral with exactly one pair of parallel sides. Yeah. So it's got one pair of parallel sides and one anti-parallel. And I think a trapezoid, I can't remember this, but it may say at least one pair of parallel sides. Because I think a trapezoid could, if it had the other two sides could be parallel, but it's just not expected that they are, right? It's not part of the criteria for a trapezoid. But in general, you'd have two pairs of parallel sides and two pairs of non-parallel sides. So if I wanted to add up the area of this thing, a good thing to do in geometry is to just kind of like cut and reconfigure in your mind. Couldn't I just take this side right here, and I'm going to hack off that little triangular piece and rotate it up there and do the same thing right here, right? I'm going to rotate that up there, and I create a rectangle out of it, which is easy to some area, right? The height would be the same. What would happen to the length of my rectangle? If the two bases were B1 and B2, when I reconfigure this, what would the lengths, the horizontal lengths of those sides be? They'd be the same, but what would they be in terms of B1 and B2? Wouldn't the total amount of lateral side have to stay the same? So if I added up the total length of the horizontal sides of that shape, they would always be B1 plus B2, wouldn't they? Right? I've just kind of cut and paste a little bit, but the total, the amount of distance an ant would have to walk to go from there to there and from there to there to traverse the horizontal parts of that shape would never change. It's just going to be reconfigured a little bit, right? Everybody agree? So that each of them is the same, then wouldn't they each be the average of the two? Right? The total length divided by 2, the total horizontal length of those sides divided by 2 would be what we would get if we had a rectangle which has two equal length horizontal sides. Make sense? So therefore we get the average of the two is the length of the rectangle times the height. Okay? Well, the same thing is true if I tip this thing sideways, right? The area of this vertically aligned trapezoid is going to be the average height times the width of the interval, right? Make sense? Okay. So then we're just going to sum those up for a whole bunch of trapezoids, and that's going to be our approximation. It's just that simple. Some good stuff happens though. When we start to do the process of adding all these things up, we can see some patterns which give us a formula which is easier to use than having to add up a bunch of trapezoids individually, right? So let's build that up. So just like before, we would take our area and we would carve it into n rectangles, right? We'd start off at A, which we could call x sub 0. And then remember what we're going to do. We're going to do the same thing as before. We're going to take steps of width delta x, n of those, until we get all the way over to x sub n, which we could also call B, the right edge of our interval. Okay? And then what did we say about, like, what is the definition of x sub I? The right edge of the ith subinterval is what? Well, okay, but it's, where do I mean, I'm taking how many steps from the left edge to get there? I, right? Each step is delta x, right? And I'm starting at where? At A. Yeah, so it's just A plus I delta x, right? That's x sub I, just like before. And what is delta x? B minus A over n. Okay? Same stuff as before, exactly, right? Okay, so what's that tell us then? Well, if we want to add up all these trapezoids, let's do that. So the first trapezoid is just going to be that, isn't it? It's going to be I have to average the two heights. So that's going to be the value of the function at x sub 0, or A, right? Plus the value of the function at x sub 1 divided by 2, right? That's the average height of those two, left and right edge of the first subinterval, agreed? Times delta x. What's the second one going to be? So that was this one. What's the second one going to be? I got to get the average height. So what's that going to be? Yeah, it's going to be the value of the function at x sub 1, so f of x sub 1 plus f of x sub 2 divided by 2. I got to average them. So you add them up and divide by 2 times delta x, right? Oops. So there's my second one. What's the third one going to be? So this guy, yeah, f of x sub 2 plus f of x sub 3, those are those heights, divided by 2 times delta x, right? And so on. I'm just going to keep doing this, right? All the way until I get to the last two. What would the last two be? Well, the second to last one would be f of x sub n minus 2 plus f of x sub n minus 1 divided by 2. I'll average those two, right? Times delta x. And then the very last one, f of x sub n minus 1 plus f of x sub n divided by 2 times delta x. Okay, well, do you see anything? Like, what would happen here if I were to do a little algebra on this? Does anybody see anything tricky maybe I could do? And I'm calculating the area by summing all the trapezoids, right? That's the TRs for trapezoids. Like, I could factor out of each of these, couldn't I factor out a delta x over 2 out of each of those terms? Everybody agree? If I do that, if I factor out a delta x over 2, what I'm left with is just f of x sub 0 plus f of x sub 1 plus f of x sub 1 plus f of x sub 2 plus f of x sub 2, and so on, right? Doesn't it just look like that? Okay, what do you notice about that sum? Do you see any patterns in there? What is it? Everything except the first and the last terms are all doubled, aren't they? They all show up twice, right? Everybody get that? That's huge. That's going to make this really easy to deal with. So then we get, this interior sum, f of everything, we're evaluating the function at x sub 1 up through x sub n minus 1. All those occur twice. Only the first and the last are singletons. And so we could just combine these into pairs of 2, right? Instead of saying f of x sub 1 plus f of x sub 1, that's just 2 times f of x sub 1, right? 2 times f of x sub 2. And if I factored a 2 out of each of those pairs, I get 2 times that interior sum. The interior sum is doubled. The first and the last term are not. Okay? So this looks like a really good opportunity for us to use sigma notation and take advantage of our, technology's ability to sum stuff, right? So we could just do that. Look at that. That is the trapezoidal rule right there, right? We get 1/2 times delta x, which is just b minus a over n, times f of x sub 0 plus 2 times the interior sum, 2 times f of x sub I, as I goes from 1 to n minus 1, plus f of x sub n, okay? The way I like to write this, I like to do something like this instead. I like to say b minus a over 2n is the coefficient that's out in front of everything times the quantity, and then I always add up the singletons first. F of a plus f of b plus 2 times the interior sum. Okay? Just like that. Okay? And that's really easy to calculate. No big deal. So let's look at a couple examples. So how about this one? If f is continuous on, and this is the trapezoidal rule, if f is a continuous function on some closed interval, then we can use the trapezoidal rule to approximate an area, okay? So what was it? See if you can remember the trapezoidal rule. Okay, so what's delta x though? Okay, good. So b minus a over 2n was the first part. That's what's out front, times f of a plus f of b plus 2 times the sum of what? Say it again. The interior values, yeah. 2 times the sum of x, f of x sub I as I goes from 1 to n minus 1. And remember, what is, we got to define that. What is, oh, go away. There we go. What is x sub I? It's just a plus I delta x, right? That's it. So we could write it as a plus delta x is just b minus a over n. It's just that, right? But what we'll do, like, we won't write it that way ever. We'll just, when we're doing trapezoidal rule, we'll just calculate what is delta x. It's just going to be some fraction, and then we know what it is, right? And we just plug it into that formula. So let's try one of these. Try this guy. What if we wanted to approximate? Now, sine x, we could do this one using calculus, right? This is an integrable function, but pretend it's not. Let's just use the trapezoidal rule. If we want to add up the area under sine x from 0 to 2 pi, what does the trapezoidal rule tell us it is for n trapezoids? So we're just plugging into a formula. What's a? What's b? Okay, so b minus a over 2n is just 2 pi minus 0 over 2n, right? So isn't that just, and we want to do it for n equals 8. Yeah, we have to pick a number too, by the way. We're going to pick a number of trapezoids. We're going to pick n equals 8 arbitrarily, okay? So then that gives me 2 pi minus 0 over 2 times 8 is 16. Well, I could divide each by 2 there, couldn't I? And just get pi over 8, okay? What's f of a? Well, it's not 0. What's f of a? A is 0, so I'm evaluating the function at 0. Oh, but you guys, okay, so sine 0 is 0. You're right. Yeah, okay, it's sine 0, isn't it? Yeah, I see what you're saying. You're right, yeah. Sine 0, which is 0, plus sine 2 pi, which is also 0 in this case, right? Plus 2 times what? The sum of, what is x sub I? Let's calculate that for our problem. What is x sub I? 0 plus times b minus a over n. What's b minus a over n? 2 pi divided by 8. That's just pi over 4, isn't it? Right? Times I. So it's just pi over 4 times I. Right? So we're just adding up that sum, right? I is going to start off being 1. So I get pi fourths times 1 plus pi fourths times 2 plus pi fourths times 3 plus pi fourths times 4. Got 8 of them, right? Well, actually, I don't have 8 of them. How many do I have? 7. I have n minus 1 because remember my interior sum stops at n minus 1. It doesn't go all the way to n. Right? Everybody get that? Okay. So that's our answer. We could use technology, though, to add up this sum, this big long sum. Right? We could use technology by just summing this, by doing sine of I times pi fourths as I goes from 1 to 7 and let a calculator do it. And if we do all that, we get the answer negative 8.72 times 10 to the negative 17th. What's that trying to tell us? Yeah, probably approaching 0, right? And it is 0. We know it's 0. Sine function that goes from 0 to 2 pi, it's got just as much area above as it has below, right? So we knew the answer had to be 0. Okay, you guys. Okay, now you go do this one. Jump to the boards and go do that one for me. First of all, write down the trapezoidal rule. Which country's going to win? USA. Okay, so you got, everybody did this, right? You got that, b minus a over 2n, and we want to simplify this stuff. 2 pi minus pi is pi, so you're going to get just pi over 200 is what you get out front. What about inside? Well, x sub I is a plus I delta x, so that is, if we plug in values, that's pi plus I times what? Delta x is 2 pi minus pi over n, but 2 pi minus pi is just pi, right? We want to make that easier. We want to make x sub I just look like pi plus pi over n times I. Make it look as easy as you can, okay? Just like that right there, okay? N is 100, so we plug in 100. Everybody get that? And then I just let technology do all that for me. Okay, and we get that, right? So, question comes up. We'll get a little more practice. Again, this is, I think in our textbook they talk about the trapezoidal rule as being the average of the left and right Riemann sums. I don't like that way. I mean, you can do it that way. It's fine, but I almost think it's more work to do it that way personally. I put this in there for your notes, but we're not going to worry about that. Here is the part that's not covered. Again, this is another thing about the AP test that's so stupid. They don't even cover this. This is kind of a big deal. How would you know how many trapezoids you need, right? How would you know? Because it's just kind of an arbitrary thing. Well, there has to be a way. There is a way. There is a way. There's the error formula for the trapezoidal rule. Here's what it is. So if the function f has a continuous second derivative on our closed interval, then the error e in approximating the trapezoidal rule is given to us by this formula. The absolute value of the error is less than or equal to b minus a quantity cubed over 12n squared. So I've got that ratio times, this is a weird one, times the maximum of the absolute value of the second derivative on your interval. That's kind of weird, right? And do you have to get it exact? No, you just have to, make sure that you're using enough rectangles that you're guaranteed to be within that error tolerance. So here's an example. Like, what if we want to determine a value of n such that the trapezoidal rule will approximate this area with an error of no more than 1/100th. Okay, so then what is our function? The function is the square root of 1 plus x squared. That's f of x, right? That's the function under which we're adding up area. So we need to calculate a second derivative. The first derivative would just be 1/2 times 1 plus x squared to the negative 1/2 times 2x, right? By the chain rule. So it gives me that. Agreed? Calculating the second derivative means I've got to do, that's going to be more complicated because now I've got a quotient rule, don't I? Or a product rule, no matter which one way or the other. If I differentiate this using the product rule, what are we going to get? Well, it turns out that we end up getting this as a result. I don't want to go through the whole process because we're going to run out of time. But you guys could all do this. We could take this derivative using the product rule or the quotient rule if we write it as a quotient. And if you did that, you would all get this result, okay? So now this is the part that's a little strange, but it's a lot easier than you might initially think. That part, right? What is the maximum of the absolute value of the second derivative? Well, if our second derivative is 1 over the quantity 1 plus x squared to the 3/2, what's the maximum value of that going to be on the interval from 0 to 1? Think about this fraction. Fractions are biggest when the denominators are what? Smallest, right? Everybody get that? So when is this denominator going to be smallest? When x is 0, right? So the maximum value of the second derivative is just going to be 1. Okay? We'll come back to this.